Hello, welcome. In this short video, let us look at the numerical implementation of an averager for continuous signals. It is given a signal x of t that goes through this averager 1 by t integral over the signal d tau, and then we get the output y of t. So the actual system function is that y of t is equal to 1 by t integral t minus capital T to small t x of tau d tau. It's like a running average of the input, but it's only taken over a window of size t. Now we want to write a MATLAB code for this process or for this system. Let us look at the numerical algorithm. So the first step is to choose the averaging time. So this value t depends on the various things. For example, it usually depends on the nature of the observations we are looking at, and then the next step is to determine the sampling rate, and then assign it to the value fs, sampling rate, assign it to fs, and then create a time vector corresponding to the time t. Time vector, because we are implementing in a digital computer, so we need a vector corresponding to time t. And then we need to note all the locations of different values of the time t, that is note locations. Specifically we need a time t is equal to 0, and at time t is equal to capital T, and at t is equal to final value of t, say something like m into t. So we need to know the discrete locations, that is indices corresponding to these values of time. The integration time t is related to the number n, which is basically its analog or its corresponding value in the discrete time, and they are related by t is equal to n into delta t, where delta t is the sampling interval, or it is basically 1 by fs. So n is the corresponding number for averaging in discrete time. Next, so in the algorithm we either the next step is to acquire the signal. So for example, in simulations we are going to use exponential of minus 2t for validation of the algorithm. So in reality it can be any observation, any vector of observations, any vector of observations. So that is the now we look at the for loop for this algorithm. So we built a for loop. We build a for loop which goes from time t equal to 0 to time t is equal to the final value, say mt. That means in discrete terms it will be starting at some value corresponding to t equal to 0 and end set the value of the index at t equal to capital MT. So the key point here is to extract the time vectors and the signal vectors corresponding to t minus t to t. That is, recall from the original definition of the averager, that is y of t is equal to 1 by t integration t minus capital T to t x of tau d tau. So for doing this numerically, we need to have the value of x of tau for these duration or this interval, and also the values of the time for this duration. So for tau is equal to, that is for tau between t minus t and t, we need to extract the time vector values, that is time values, and x of tau value. So this works as follows. So here we have 0 and here we have t, and then each little box is basically corresponding to delta t. So for doing integration at time t equal to 0, we have the values from minus t, this is minus t to 0. That means we have to take these values from this location, that is at n minus 1, that is minus of n minus 1, that is at t minus t plus delta t, that is at this location to 0, or minus of n minus 1 to 0. So we take these values and then we take the corresponding values of the signal x of tau and we do the integration. And for the next step, so for the first iteration in the for loop, we have values from here to 0, and for the second iteration we have values from minus of n minus 2, that is 2 minus n to 1. So initially it will be 1 minus n, or n minus of n minus 1 to 0, and then it will be in the next iteration it will be 2 minus n to 1, and then 3 minus n to 2, and so on, it goes on. and in general at any location, say tx, that is, let us say this is tx, that is a discrete location, then it will be tx minus n, it will be tx minus n plus 1 to tx. So that will be the general interval. So once we have the time value, the time vector and the corresponding signal vector, all we have to do is we compute the numerical value of the signal at this tx as 1 by t multiplied by trapezoidal integration with respect to time vector, say tv. tv is the time vector corresponding to this interval, that is from tx minus n plus 1 to tx. So tv will be like t of the time vector t of tx minus n plus 1 to time vector of tx. So that is the vector. So tv, and then we have the x of tau, that is the values corresponding to this interval. So we do this integration and we put this in this vector, that is ynm of tx at this location tx, and then we can plot it, and the next step is to plot the results. So for example, when x of t is equal to exponential of minus 2t, then y of t, that is its integral, that is averager, is basically given by e power 2t minus 1 by 2t multiplied by e power minus 2t. So that is the integral. So y of, that is the average. So we can plot the results from the numerical implementation and compare it with the theoretical value. Now let us look at the MATLAB code. So our goal is to implement this into this averager. So we develop an algorithm. So we choose the time t, that is the averaging time, and then we choose the sampling rate, and then we choose the length of the total interval, I mean the value of m, so that we can create a time vector, and then we note all the important locations of time, so that we can, for example, decide the length of the for loop, that is a number of iterations in the for loop, and we can also decide the length of the integration time, that is in terms of discrete values. So that means the value n. So and then we discuss, for example, in this algorithm we decide the signal to be exponential of minus 2t, so we use that, and that is we generate that signal, and next we design the for loop. The time vector is given by t of tx minus n plus 1 to tx. So that is the value of the time, and then the signal for corresponding to this time is then temporarily stored in a vector temp. And then we do the integration. We get the numerically computed average value, and then we also construct the theoretical value for this vector. That is we also write the expression for the theoretical value of this averager. Finally, we plot both the theoretical curve and also the numerical values. So the red one gives us the theoretical curve, which is basically e power 2t minus 1 by 2t d power minus 2t, and then the blue dots or blue circles basically gives the averager value computed numerically, that is by using our algorithm. So we can clearly see that there is a perfect agreement between the theoretical calculation and the numerical calculation. So to summarize, in this video we have looked at the numerical implementation of an averager for continuous signals. That is, we want to implement the formula y of t is equal to 1 by t integration t minus t to t x of tau d tau. That is like a running average of a finite duration of a signal, that is, and then we developed an algorithm for this purpose. So the algorithm has the following steps, that is, we have to choose the averaging time, sampling rate, create the time vector, and then note the locations of important values of time, and then for example for validation, next for validation we choose a particular signal, say exponential of minus 2t, and then we write the for loop. In this for loop, most important thing is to note the corresponding values for the time vector and its signal, that is corresponding signal. So we have to note the values of the time, say for example at t is equal to 0 we have values from minus t to 0, or actually from 1 minus n to 0 in terms of indices, discrete indices. So we note down the time vector, and then we also extract the corresponding signal, and then we do the trapezoidal, that is numerical integration by using the trapezoidal formula. So we get, and then we divide with time t, the capital T, so that we get an approximation of the averager. Sorry, we get an approximation of the average. So then we store it in a vector ynum, and then we also have the theoretical average value that is given by e power 2 into capital T minus 1 by 2t into e power minus 2 into small t. So that is the theoretical value of the averager. So we compare these two results in finally we compare these two results. So we look at the MATLAB code. We have built all these steps in MATLAB, and then finally we plot the results, that is both theoretical curve and the numerical results. So we see that there is a clear agreement between the theoretical result for the signal e power minus 2t and the numerical value of the averager. Thus we have implemented the averager for a continuous signal in MATLAB. Thanks for watching.